In this video, we're going to be talking about air conditioning with airside problems. Okay, now by air system problems, we're talking about blower motor, duct work, filters, anything that is affecting the airflow through the system. So why do we want to look at airflow? It's a primary problem that can occur in any air conditioning system. Okay, we want to make sure we don't have a reduction in airflow, and we want to make sure we don't have too much airflow. Air handling systems do not suddenly increase the amount of air across the coil, nor do they decrease with proper maintenance. A refrigeration system does not increase heat transferability based on airflow. Okay, I mean, it's going to have the ability to remove the same amount of heat, but the airflow makes a tremendous difference in the comfort and the efficiency of a unit, and we'll talk more about that as we go further. There's some magic numbers we want to make sure everyone's aware of before we delved into this. First of all, 400 CFM, that's 400 cubic feet per minute of air per ton of air conditioning. So a 1-ton system needs 400 CFM of air. A 2-ton system needs 800 CFM of air. A 3-ton system needs 1200 CFM of air. A 4-ton system needs 1600 CFM of air, and a 5-ton system needs 2000 CFM of air. So those are the bases. Now you're going to run across 1.5-ton systems. They would need 600, 2.5 would need 1000, 3.5 would need 1400, and so on. And you can multiply up from there. But those are the key. This is a very important number to remember. Now, we also have to realize the data plate cannot be ignored. There's a reason why the data plate can't be ignored. It's going to give you a lot of information. Okay, so if I come here and take a look at my pen color, okay, I want to real quickly highlight a few things. Okay, in the model number, we have our size of air handler. Okay, so this is a 48,000 BTU per hour air handler. So that's going to be a 4-ton system because we have 12,000 BTUs per ton. Now, I did white out the serial number here because of privacy issues for where I took this picture from a customer. Okay, so, but the serial number normally contains a date code. Now, in the case of this manufacturer, they put a date code right on the air handler. It tells us when it was made. The refrigerant is there, and our design pressure for the coil is there, okay? In other words, when we're testing this for leak checking, we would never go above 450 psi, okay? This is a heat pump system, by the way. But more importantly to me is the motor amperage, the full load amperage on the motor, and also what our design static pressure is, otherwise known as test static pressure. It may say external static pressure. Different manufacturers say different things on this. Okay, so there's a lot of information on this data plate that I want to know about. And even though when you're out testing, it's sometimes nice to know what voltages you're dealing with. But we're not going to talk about the motor side right now, except with how it relates to airflow. So the model number gives you the size information. The serial number includes the date of manufacturer. The refrigerant design, the motor amperages, and static pressures are all part of the data plate. All extremely important. So before you start testing some airside, you have to have some tools, okay? You can't just walk in with a screwdriver and minimal tools. You have to have a static pressure tube or pitot tube. You got to have a manometer, could be U-tube, could be electronic. You need an amp clamp for your meter. You need to have a wet bulb and a dry bulb thermometer. Okay, I like using the combination. That's why it's on one line here. I always also have a second dry bulb thermometer because I like taking my temperature readings all at the same time. You need to have your eyes and ears. I'm going to tell you right now, that is probably the best tool ever because you can hear airflow problems once you start getting used to it. And we want to have a wet bulb, dry bulb, delta T chart, okay? Temperature split chart based on wet bulb, dry bulb. We'll talk more about that. The first step in checking for air system problems is to take a temperature reading across the evaporator coil. In other words, what you're going to be doing is you're going to be taking a temperature reading of the return air and the supply air. You might as well take your wet bulb temperature also at the return air. It makes a difference. But the difference between the two dry bulb temperatures, that's supply to return, is called temperature drop. Most of the time, an acceptable temperature difference is between 18 to 20 degrees. However, with newer systems, it's very important to look at wet bulb on the return side. So either your wet bulb, your electronic probes or sling psychrometers used to measure the return air, dry bulb, and wet bulb temperatures. Okay, and again, we can get electronic psychrometers right now, and those are what I remember, what I more am apt to tell you to use. These measurements, okay, all of these measurements together will help you determine if the problem is a result of improper airflow or refrigeration system problem. Now, a few minutes ago, I mentioned a wet bulb, dry bulb temperature split chart. Okay, this is just an example of one. There's many of them out there, but they're basically the same thing. Okay, so you take your indoor dry bulb temperature, okay, you take your indoor wet bulb temperature, and it will tell you what the required supply air temperature is. In other words, if I have an air conditioning system that my return air is 76 degrees, okay, we use the 76 column, this is dry bulb, and if I measure a wet bulb of 68 degrees, that means my supply air should be 61 degrees. Okay, so that's exactly a 15-degree temperature split. Now, if you do not measure 61 degrees, okay, on your supply air, that's dry bulb, okay, you're gonna look and see, is it hotter or cooler than the required supply air temperature? If the air exiting the duct is 3 degrees or higher, cooler than the required supply air temperature, the airflow is too low. Now, don't just turn up the motor, look for what the problem is. Replace the filter, clean the evaporator, clean the blower wheel, and at a last case scenario, increase the blower speed. However, okay, you do need to find out what changed, because if this system was working properly with all the speed settings the same and everything for years, and all of a sudden there's a problem, something has changed. If the temperature is higher than required, okay, the system has too much airflow, or is low refrigerant, or has weak compressor valves. Don't just jump over to low refrigerant or weak compressor valves. Look for leaking ductwork. Okay, there's some reason why the air is moving too fast. Again, if it's worked properly for years, something has changed. If the actual air temperature drop is greater than required, then the air quantity has been reduced or slowed down. This could be due to dirty filters, dirty evaporator, problems with the blower, or unusual restrictions in the ductwork. The most common cause of restrictions is the air filter. Okay, now I don't normally go do my readings before I look at the air filter. That's like my first stop. Actually, second stop. First stop is thermostat, second stop is the filters. But air filters are the throwaway type. You know, people are saying 2-3 months. Some people say 1 month. Okay, look at the situation. However, if it's someone that has pets, if it's someone that has a dusty house, don't tell them your house is dirty, you need to replace the filters every month, but just suggest that they replace the filters more often. Now, someone did a study at one time, and I think it was the U.S. Department of Energy, that looked at the system efficiency lost based on visible filter condition. Okay, so if someone has a $300 a month cooling bill, which is very possible in the South, okay, and if they have a pretty dirty filter, they can be increasing their cooling costs between $100 and $120 a month. Okay, so the filter condition has a direct relationship to the cost of cooling a house. The next thing you want to look at is the blower motor and drive. Okay, you want to check that the blower motor and drive, in case of belt-driven motor, you want to make sure that the bearings are properly lubricated and operating freely. If belt-driven, check the belt for dry rot and cracks. Cracked or heavily glazed belts must be replaced. Heavy glazing can be caused by too much tension on the belt, driving the belt down into the pulleys, okay, and then it overheats. Proper adjustment requires the ability to depress the belt midway between the pulleys, approximately 1 inch. Okay, and on smaller motors, it's actually 1/4 inch. Blower wheel needs to be clean. The dirt accumulation on a blower wheel can sometimes fill the area on a cup blade, allowing it to spin freely, but it can really reduce the airflow. If the wheel is dirty or has mold buildup, it must be removed and cleaned. Attempting to clean a wheel in place is never recommended. Don't try brushing because a poor cleaning job will cause imbalance to occur in the wheel. Extreme vibration and noise will result. Other damage may result, such as damage to the motor itself. You always want to take blower motor amperage readings when you're doing airflow diagnostics. Now, be aware if you take with the door off, okay, in other words, you have the blower compartment open, you can see the motor, and you can see the blower wheel. Your amperage will always be higher than with the door on. Why? Because air has weight. When a blower is moving a lot of air, it's going to draw more amperage than when it's moving less air. Air is heavy, so that weight of the air, the large availability of air, and attempt to push that much air through the ductwork, okay, is going to draw more amperage than when it's moving less air with the door on. Okay, in this case, you'll see that I've clamped onto the common wheel of a motor, and I'm getting a 4.79 amps. Now, when we looked at the data plate earlier, okay, that was the data plate of the unit a few slides back, we were seeing a data plate full load amp of 6 amps. Okay, so we're fine on this motor, because once I put the door on, the amperage is going to drop a little bit. Now, don't think this picture is normal, because there are some issues here. That capacitor is just hanging on the wires. So there are a few issues here. Okay, so this is the example of the left-hand picture is an extremely dirty blower motor. Looks like someone's cat sort of crawled up into it and never got out. But this will happen in a very dusty environment or someone who's never cleaned it. The right-hand picture here, this was actually in a Florida area house where you start seeing mold buildup on the blower motor, on the wheels itself. Okay, and this little cup in here, you'll see that the dust caked on the left-hand picture. What it's doing, it's caking in that cupped pattern of the blower motor, of the blower wheel. Okay, now again, if you come across something like the picture on the right, you cannot tell someone it's mold because you don't know. Okay, you have a suspicion it's mold, and you're probably right that it is mold. But do not ever tell a customer they have mold without doing laboratory tests to confirm that it's mold. One of the next highest issues that you see is unusual restrictions in ductwork. Okay, now placing furniture or carpeting over floor return grill greatly reduces the air available for the blower to handle. If you block return grills, especially in where you have two-story construction and the return grills are on the floor, okay, you can actually significantly reduce the amount of air that's available. The other thing that happens very frequently, especially with people who've retired or who have closed off part of their house because no one's living in it anymore, okay, they shut off the air to the unused areas. Well, this greatly reduces the air over the coil. I know one customer who shut off the air to 4 bedrooms that are no longer used since their kids moved out. So all of a sudden, we've taken and cut the size of the house basically in half. Okay, and we've cut in half the amount of CFMs that are available to go after the coil because air has to go someplace. You shut off the registers in an unused space, all of a sudden you can't push that air to any place. So you've reduced airflow. Covering a return grill to reduce noise from the unit itself may reduce the noise, but it will drastically affect the operation of the system by reducing air quantity and quality. The condition of the air grills and vents can indicate potential problems. Water stains can be caused by improper humidity conditions. Soot stains may be the result of improper functioning furnace exhaust leaking back into the air supply line. The collapse of the return air duct system will affect the entire duct system performance. Air leaks in a return duct will raise the air temperature and reduce the temperature drop across the coil. You want to look out for pinched ducts, sharp bends, and unnecessary duct length, especially if you have flex duct. Here's some problem scenarios. Okay, the one on the top left, you're missing a whole bunch of insulation. Okay, not just the outer cover, but down here where my mouse pointer is right now, we're missing insulation. Here too. Here we have a duct being held up, it's coming down, so someone put a strap in, but it's a severely kinked duct. There's no way the air is flowing normally through that. Bottom left, again, more missing insulation, and the internal component is open. Okay. Keep an eye out for other safety issues. The picture on the left has nothing to do with airflow, but it is a problem because you now have a sealed tight exposed wiring. But the one on the right is the one I really wanted to show you, okay? You have a filter in the back of an oil furnace that looks like it has never been changed. You can actually, if you look close on it, it's actually pulling in. Here's some more sharp bends and excessive flex duct length. Okay, you see how the one on the left is actually doing a 180-degree turn going over the ductwork. The ones on the right, those flex ducts were just basically come in boxes of 25 feet. And regardless of how long it was, they used a full box for every length. They didn't cut it back. Iced up evaporators tell you there's not enough airflow for the most part. Okay, could lead to a refrigeration side problem, but most often it's not enough airflow. Okay, we're going to basically skip over this one, but again, iced heat pump, it's not going in defrost. I'm going to skip that. Look out for issues. Again, it's airflow, but most often it happens in the spring in the cooler climates. Condenser coils are covered. So let's take a quick look at a series of pictures, okay? These are pictures, for the most part, all on one job. And we can see how many airflow problems you can find. Okay, this just happens to be a gas furnace in an attic, believe it or not, of a condo unit where the air conditioning coil that you can barely see over to the left was added as an afterthought. Okay, so we have our supply duct coming out of the furnace. It's coming over here to a coil. We have our return duct down here. We have a natural draft water heater right here. Okay, so we have a few problems right there to start with. Okay, so how many problems can you spot in this picture? Okay, again, we have a natural draft water heater sitting right in front of a very old return duct, and this is a very, you can't see it from the picture, but this is a very loose fitting cover on the blower housing. So it's a very likely possibility that we are sucking some of the exhaust gases from the water heater back into the furnace. Okay, and it's even a more possibility when you look at the condition of the return plenum. Okay, this is all return plenum. It's all duct board. Okay, and over the years, you can actually see where people have done it. Tool bags have been sat on top of that ductwork. Okay. Now, when we look at this picture right here, this is the coil. My furnace is over here. Okay, I'm coming up out of the furnace. I'm expanding my ductwork to come through the coil. What do you see on the other side? So right here, whoever did the right side of this did a nice job of a transition into a coil. While the top's a little rough, but still, we're having a nice transition into a coil. Over here, though, you could see that the cut out of the coil is much smaller and squared off, okay? So we're coming out of a nice transition. We should be coming a similar transition back into appropriately sized ductwork, because air does not like sharp corners, okay? It doesn't like coming through here and hitting up against a wall. Okay, that will affect the entire airflow. Okay, now notice the size here and the size here coming out of here, we're dropping in size. The other issue is I have an air duct that is looped over here, okay, to feed some registers on this side, and I'll show you more of that in a moment. Okay, so we come out of our air conditioning coil right here, we go into a round, and then we transition back to fiberboard, okay, plenum. And again, here's that one poor duct that comes back all the way up that way. Okay, now this is my plenum. Again, my furnace is over here to the right, so I transition to that plenum. This one is just nothing's connected to it, so we don't worry about that. Okay, but see this piece of one duct takeoff coming off that end of that plenum. Okay, I have a kink here, I have some restrictions here, and then I go into a grill right over here. Okay, that is a very loose, someone took a 25-foot piece of flex right out of a box and just attached it on both ends. Okay, another branch of the same system. Okay, if you look closely over here, you'll see that this is not you see how these come off nice and straight off the takeoff? This is all flex duct. What happens over here? This comes off the takeoff, drops down, and that is severely restricted right as it drops down. Taking a look at the blower motor and the blower wheel, you can actually, on the picture of this blower wheel, see the cupping, okay, and see that all of this dirt and dust and debris is built up on those cups. This blower is not moving a ton of air. Okay, now with the exception of the probe where I actually found a piece of tape where someone else had taken some readings at one time. Okay, this is a supply duct reading where I'm taking. Okay, but notice how this comes out of that supply plenum on the left side of the coil and drops straight down. Okay, this ductwork in here, just because of how it's tipped over, is severely restricted on the supply side. Can't see it very well, but the filter is also pretty clogged, and the customer here has a very nice and clean house, but this filter is severely clogged. But so if you go through this system that we just looked at, okay, the system needs to be cleaned, probably needs totally new ductwork, because, or at least tightened up, because everything is sagging, everything has some restrictions. Okay, needs a new plenums on at least the left side of that coil. Okay, needs a new return plenum. And probably needs to take a look at where that water heater is with respect to the return of the furnace. If it needs to stay there, it needs to be sealed 100%. Now, the reality. Okay, this is a 1988 system. They're probably going to replace it. They need totally new ductwork when they do. So airflow problems you can find on just about every system. It's an evaluation of how much they are affecting performance. In this system, the airflow was half of what it was supposed to be. And over the years, the charge of the refrigerant actually had been adjusted to account for the lower airflow. So they were doing their temperature readings, they were taking their required readings, but they were actually adjusting down the refrigeration effect in the unit rather than fixing the airflow. Airflow is important.